Okay, excellent. In that case, Cyril would like to begin by acknowledging that this workshop is being broadcasted from Surrey, British Columbia, Canada, located on the traditional and unceded territories of the Coast Salish peoples. So without further ado, we are Cyril, and we are proud to present this year's challenge. This is Workshop 2 in the Planetary Exploration Challenge series, and Surrey Robotics Innovation Lab is a nonprofit organization dedicated to empowering youth innovators through robotics and STEM, as you are now about to begin. All right, what are we doing in this workshop? Well, we're going to look at a brief history of computers really quick. It's the brains of our robot and the thing that makes it work. We're going to look at the programming logic, if, else, and, or, and while loops, in addition to other forms of programming logic that we may want to implement in our codes. We're going to be applying some knowledge of sensors. We are also going to be experimenting with types of mazes and simple maze solving algorithms. So before we get to that, we'll just do a little bit of an update. First of all, the planet has changed a little bit. We noticed there were a few problems with the sensors and the black obstacles and a little bit of miscommunication with the 2D map. As a result, we've created a 3D render of the map that you will be playing on. Most of the key differences, the obstacles are now red instead of black. If you've been playing with VexCode VR, you may have noticed that the Vex robotic sensor does not have black. So we've made it red so it's easier for you guys to program. Additionally, there are walls now on the collection zones for samples. Now they have blue walls, so the front color detection sensor will be able to detect them. These walls can be run over and knocked down and driven over, so you don't worry about hitting these. The inside of these walls will be painted green. This will indicate you can drive through them as well, and it might help you in navigation. The parking zones are still yellow and do not have any walls, so be careful here. You're going to have to monitor your robot's position elsewhere for the parking zones. They are still yellow. Now, the robot has also changed. You guys have had an input on you wanted a different location of the sensor and the color sensor in particular. So we'll now allow you to choose the location of your color sensor. You can have it facing forwards or you can have it facing down. Now beware, depending on lighting conditions within the map, the downwards facing color sensor may not always be able to calculate the correct color. Nonetheless, it should work enough to give you your results, and we are now allowing you guys to choose whether you want it to be forward facing or downwards facing. It'll be mounted in the same location, just in a different angle. If you want the downward facing one, please add a comment to the start of your code saying that you would like a downward facing color sensor. This will be covered on later in this workshop, but in the time being, if you do not specify you want a downward facing sensor, it will always be a forward-facing sensor. That is its default position. All right, so let's get to the workshop. I guess before we get into programming, I shall ask the question, what is a computer? I know it's a bit difficult. We've got these smartphones in our hand. Is this a computer? Is this a computer? Or I don't think you can see it. It's actually a calculator. Or is this a computer? Oh, you can't see anything. Is this server a computer? What is a computer? Well, that's a question I will ask you guys. All right, Daniel, if you will activate annotate, we can let them write on the screen, scribble what they think.
Sure
Let's see
thing.
if you know what exactly a computer is.
All right, guys, yeah, feel free to draw.
And if you could not find the annotation buttons, unfortunately, I cannot. Oh, there it is. The annotation button should be at the top of your screen or near your pause, show video, mute buttons. It should be up there. You can click that and it'll let you write and draw on the screen. Someone has put a square around compute. Okay, so what exactly is computation then? Ooh, I like that. I think I'm reading someone. I think someone's trying to say there can follow instructions. It's a very good point.
Hmm.
We do need to put inputs into computers. That is correct. Let's see if anything. Oh, no. You didn't see that next slide. That never happened. Daniel, is there anything in the top right corner? I can't see it. And I can't click my screen.
No.
All right. Is there anyone else that might have an idea on what a computer is? It's a very difficult question to answer. It's kind of gotten convoluted over time. Convoluted is just a big fancy word for mishmash combined. Interesting. Ooh, can make calculations. I like that.
Yep.
Yeah. So does that answer the question? Is my calculator a computer? It technically does calculations. Well, let's find out. Daniel, if you could clear the screen, we shall now move on to answering this question. So let's go way back. Before we had electricity, in fact, the earliest computers were actually mechanical. They use a series of gears and physical components, levers, rods, pistons, anything that moves, and they could do this to make calculations occur. Now, of course, they could only do a specific task. They're, as mentioned, completely analog, which means there's infinite values and infinite outputs. You can have any inputs. Let's say I can put in pi into my computer if I wanted to. Pi is an infinite number. It never ends and never repeats itself. I can put this into a mechanical computer and it'll spit out a number equally as infinite. It's completely analog. Now we're going to look at a few examples. First of all, if you see on the right of this page, we have the Antikythera mechanism. Now, this is an ancient computer found, I believe it was near one of the Greek islands, or it was Greek or Roman, or I don't remember, one ancient device. This was dated by scientists to be about 2,100 years old, or 100 years before the Common Era. As you can see in that drawing, you've got this really weird bunch of colors. Those are actually all gears, really, really fine gears. And you might not be able to see what it does, but this is actually an ancient mechanism that allows you to know the location of the planets through time. So you would tell the date that you're trying to look at, and this machine, by spinning gears, will allow you to know where the planets are at any given time. Pretty interesting technology for something built 2,100 years ago. It's still a mystery on how they built it today, and it's only a recent discovery that we're starting to begin to research. So let's talk about some other things. Here are some more mechanical computers. Behold, the 1837 analytical engine. This giant contraption here is actually just a calculator. You use a whole bunch of dials and cranks to put in the number, then you do that crank as that person is, spinning it around, and it'll spit out your answer. Another mechanical computer is the tide prediction. I can't see my slide again. The tide prediction machine. So this computer actually does calculus. It actually can do integrals and derivatives. And this is actually used to predict the global tide patterns. If you think about it, ships have to travel in and out of port. If the tide's too low, they might run aground or they can't get in. So they created this mechanical computer, which you can program simply by moving some elements around, adjusting some dials, and cranking to calculate the tidal patterns anywhere within the world. Now, if you have more curiosity about this particular machine, there's a YouTube channel called Veritasium, which has an excellent video on explaining how these mechanical computers work and how you can get a ball or a cylinder with a little pen on it to do calculus for you. That is the wonder of the mechanical computer. Now, again, like I mentioned, these computers are really basic mechanical components. They're completely analog. But today we enter something called digital computation. So let's take a look at that. Let's go fast forward. Oh, yikes. Let's fast forward about 1,900 years or so to the 1940s. In this particular time, 1945, we made something called ENIAC. It's actually a huge computer about the size of a townhome, and it contains 18,000 vacuum tubes. These are the precursor or the predecessor to what we now know as transistors. Now, ENIAC, as some of you may see now, is actually an acronym: Electronic Numerical Integrator and Computer. So, what a fascinating piece of equipment this is. Now, you might be wondering, so that's a massive computer. How much computation can it do? Well, it's probably less powerful than your cell phone by this point. In fact, zooming another 100 something years into the future, well, no, we're not even 100 something years in the future yet. But today, we're doing some pretty weird stuff with our computers. We're doing quantum computing. We've shrunk these transistors to the size where they're tiny and tiny components. And if you see a microcontroller and IC, I had one here at one point. But if you ever taken a look at your computer chip, that CPU chip has millions, if not billions, of transistors. Those 18,000 vacuum tubes inside of the ENIAC, well, your computer basically has the equivalent of that, but it has billions of them now. Same thing as in your phone. Your phone also contains millions of these transistors. They can do so many more calculations so much faster. And technology has been going absolutely insane. Your gaming console, there's actually a company out there, or I don't remember who, but someone has actually taken a whole bunch of Xboxes and built a supercomputer by linking all of these game consoles together. It's absolutely insane. So that's what's happened to our computers today. But now to answer that question, what exactly is a computer? Well, as we've seen here, all these items have in common, they take an input, they have an output. They do some calculations, they use a little bit of logic in between. You take numbers in, you spit numbers out. That is the definition of a computer. So your cell phone, technically a computer. Your calculator, technically a computer. They all do exactly as specified. So how do we interface with a computer? Well, we'll just quickly look back at ENIAC real quick. In that time period, you had to plug things in, unplug things, move plugs everywhere. You have cables going everywhere, and each of these programs computer to do a slightly different task. Well, thank goodness I don't have to mess with all those hundreds of cables anymore, because I can use something called code. Now, code, of course, needs to contain something called logic. So, what exactly is programming logic? Well, our digital computers today, digital meaning it thinks in ones and zeros, yes or no. And you can think of each of these items, known as a bit, as like you're flipping a switch. You have power on and power off. Power on is yes, power off is no, or vice versa. We make these decisions using logic gates. So let's take a quick look into this. As we mentioned on the right here, we have yes and no. Zero, if you put 0 in, you get a 0 out. If you put a 1 in, you get a 1 out. But if you add a NOT gate, this is a type of logical operator that actually flips it. Now, yes is no, and no is yes. Welcome to the weird world of programming and bits. We're not going to bore you with that, but we're going to keep going. So we have here our common logic gates and OR gates. AND gates mean you have to have both inputs on to get an output. If we only have one item here, as you can see, you have two inputs, A and B. Unless both inputs are 1, which is true, we will not be able to get any output. Your output will always be no until both switches are turned on. Likewise, an OR gate does the exact same thing, or not exactly, but works in a similar manner. If you think about it, when you say OR, you can have one or the other or both. So as a result, this type of logic gate will let you use input 1, A, or input B, and it will return true. Or if they're both on, it'll become true as well. It'll only be false if both items are off. Neither or XOR gates are basically the exact same thing as an OR gate, but now if both switches are toggled to true, you don't get an output. I mean, these are your typical logic gates. You will rarely ever use NOR gates, NAND gates, XOR gates, or XNOR gates. These are not very common. Your most common ones are AND or, which we will focus on. But this table is here in the case that you want to do some weirder stuff. Also, I was wrong there. XOR and NOR gates are completely different things. Do not mix them up. XOR is, as shown here, it's an OR gate without the dual on condition, and NOR gate is when both are off. So I mixed those up, my apologies, but this is the weird world of programming logic. But we're not going to go too deep into that. That'll be your problem in university. Have fun. All right. So I feel it's time to start playing with some code. So at this moment, I will hand it over to Daniel, and he will go over some VEX code coding with this new programming logic. Take it away, Daniel.
Thank you very much. You're right. So as you may recall from the first workshop, we are going to be using VEX Code VR to program our virtual robots. So let me bring up VEX Code VR, and I encourage you to follow along on VEX Code VR on your own computer as well, if you want. So here it is. Hopefully everyone can see my screen. We have the VEX Code VR interface. This is the first thing that you should see when you first go to VEX Code, when you go to vr.vex.com. So for this first activity, I'm going to run it through with you guys, and it's going to be a maze. So if you go to select playground, we are going to be using the wall maze for this activity. So you open this, you can see it's a maze, and it has these walls here that go like this. And your robot starts on this tile right here, and the destination or the parking spot of the robot is this checkered board pattern here. So the goal is to program it so that this robot will navigate itself to the checkered board pattern automatically or autonomously. Now, the easy way to solve this maze is to just hard code it, right? So what I mean by hard code is you tell the robot to move forward by this much, and then move, and then turn left and move here, and then go here, and then here, and then here, and then here, and you know, just take, oh, and then here, and then here, 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 all the way to the checkerboard pattern. And that would be one way to solve it. But it's not the most, I guess, intelligent way for the robot to solve it, because what if you have a different maze now? Then it wouldn't be able to solve it because the walls are in a different place and the parking spot is in a different place. So that's why in programming and in robotics, it's often useful to make an algorithm or a program so that your robot can automatically solve the maze. So that's what we're going to do. So the kind of algorithm that we are going to look at today is called the right-hand rule, or as some people may know it, it's also called the right wall follower. So what it looks like is the main idea of this algorithm is we want it to turn right, and we want to check if there's a wall, and if there's a wall there, it's going to block your robot. So then you're going to turn right again. If there's a wall there again, then that means, you know, you're in a corner, you're in a dead end. So you want to then turn left, right? So you would go left, and then you would do the whole check again. You would do the right hand check, the right hand check, the left hand check. Basically, you're just using it as a way to check if there's a wall. If there's a wall, you don't go there. But then if there's no wall, then you go there. So eventually, the robot's going to eventually go to the checkerboard pattern, but just by checking one step at a time, is there a wall or is there no wall, right? So, yeah, so I'm just gonna get right into it. So what we need to do is we need to use a conditional. We need to use an if block, right? We want the robot to say if it's near a wall, then we want to turn right. So how are we going to translate that into a code? So if it's near a wall, we can use, for example, the eye sensor. So we're going to use the eye sensor today. So I'm going to bring out an if block right here. If, okay, and then I'm going to bring out in sensing the eye sensor, front eye, the front eye sensor right here. Okay, so I'm going to put this condition inside here, okay? So if the front eye sensor of the robot is near object, that means the robot is about to hit a wall, right? So if the front eye is near an object, then what we want to do, we want it to turn right by 90 degrees. Okay, so let's do that. Let's go to drivetrain, turn right for 90 degrees. Okay, so there we have that. So what if the robot sees a wall and it turns right, but it sees a wall again, right? Then it's kind of stuck in a corner. You can imagine it's like an L shape. It's stuck in a corner. So we need to handle that situation as well. So we can drag in another if statement block. So let's go to control, if, and we're gonna put it right under here when it turns. We want it to check right away, right? So let's bring out the front eye sensor block again, right here. All right, and let's do a little bit of thinking. So the front of the robot is running into a wall, so we don't want to go forward, right? We want it to turn right. So it turns right, and then it sees a wall again. So what do we want it to do this time? Well, this time we want to turn 180 degrees. We don't want it to turn 90 degrees again. So, and you'll see. So 180 degrees here. Turn right for 180 degrees. Okay. All right, so we have that. So this block, or this group of blocks right here is one main part of our code. It's the part of the code that makes the robot not crash into walls. Okay, so when it sees a wall, it's going to turn. If it sees a wall again, it's going to do a double turn to make sure it takes the right path, because there are only so many paths you can take. So next, we're going to want the robot to keep running this code while it's not at the destination, right? Like as long as it's not at the destination, we want it to keep solving the maze, right? So we should use a while block. So where is the while block? While right here. While, and then we want the robot to keep doing it while it's not at the checkerboard, while it doesn't see red. So what should we do? We should say while the down eye sensor doesn't see red. Okay, so that is going to be while the down sensor doesn't see red. So I guess we need a not operator. Okay, so there we go. This is an example of one of the logic gates that Clement just mentioned a few minutes ago. So while not, and then where is the down eye sensor? Right here, or not this one, this one. So, and then we want to switch it to down eye, because as you can see, we are looking at this map in a top-down view, right? So when the robot is at the checkerboard pattern, it's gonna, the eye sensor will, we want the down eye sensor to be the one that's looking at the checkerboard pattern. So while the down eye sensor is not seeing red here, we want it to keep solving. We want it to move. We want it to move, right? So let's put a drivetrain here, and we know that each block is approximately 200 millimeters. But the thing is, if we don't go a little bit more than 200 millimeters, it's not going to detect it. So let's put like 250 there, 250 millimeters. And then each time it goes forward by one cell, we want it to turn and get ready to check, right? So we will say turn right for 90 degrees. All right. And so it goes, so while it doesn't see red, it goes forward, turns 90 degrees, and then we still need to check, right? So we need to check if there's a wall. So we go control again, we go if statement again, if front I, let's see. Oh, hold on a minute. We shouldn't have put this here, my bad. We need to, we can't go into, we can't make it drive right away. We need to make it meaningful. We need to check something and then make it drive. So it's going for, so it doesn't see red yet, so we want to solve. So is the front eye not near an object yet? Okay, so let's go here. Let's go here. It's not near an object. So let's go here. Right here. Okay, so let's see if this works. So it doesn't see the checkerboard, which means it's not there yet. And then if it's not near an object, then we want it to move forward and turn, right? Move forward and turn, move forward and turn, check if there's a wall. Okay, that makes sense. Okay, so we have a condition for if the front eye is not near an object. It means there's space to go forward, right? So that's why we are saying drive forward for 250 millimeters and then turning. But what if the front eye is near an object? So let's add another if statement. Okay, so right here, if the front eye is near an object, so that's going to be this one. If it's near an object, then we want it to turn left. Turn left. Yeah. And then what else? What else do we need to add? So it's not near an object, we go forward. If it's near an object, we turn left. Let's add an else. Let's add an else. What if none of these conditions are true, I guess? So let's add an else. Let's see, where's that?
It has to be part of a block.
Yeah, I guess
one of the blocks for if else.
Yeah, that's right. So okay, I can't use this. I'm gonna drag this up then. So instead of this if then block, we need an if then else block that comes like here. So I'm gonna replace everything and plus put all of this back here, put this back in here. Okay, and then we need an else, because what happens when none of these conditions are true, right? We need something for the robot to do. So else, turn left for 90 degrees. All right. And then before we run this, because I think this is it. But before we run this, we we can set the speed of the robot. You don't have to do this, but you can if you want to make it go faster or slower. So let's say set drive velocity and set turn velocity right here. So by default, it comes at 50%. So I guess if you want to go faster, let's put it at 100%. All right, I'm gonna run this and I'm going to see if it works. All right, let's go. So I'm gonna click this start button here. All right, the robot is moving forward. It's checking if there's a wall. If there's a wall on both sides, it turns left instead of right. And there's no wall there, so that's why it went straight. And as you can see, it's moving one cell at a time, moving one cell, doing the right hand checking thing. And you can notice every time it hits a corner there, when there's two walls, when you make two rights and there's a wall every time, it instead turns left. Yeah.
Now, as you may notice, it's probably not the most efficient way to do things. It does take absolutely forever to get your robot from the start to the finish, and you're wasting a lot of moves, as you may notice that we're making unnecessary turns if you were to solve this by hand or with a remote control. That's why we typically use sensors to confirm our location instead of having them primarily solve things on its own. But as we can see, the robot has navigated its way to the end.
Yep. So this is probably I would say this is kind of tough to write this kind of algorithm on your first try. Uh but I just wanted to give you a taste, right? I wanted to give you guys all a taste of what kind of the most simple robust algorithm is, right? Because with this, it doesn't matter what maze you're in, your robot's going to be able to solve it eventually. Like it might be slow, it might be fast, but it's going to be able to do it. So that's what an algorithm is. It's you're able to give it different parameters, but it's going to be able to crunch the numbers and the logic, and it'll work out eventually. Now I will say, for this challenge, the final challenge when you're programming your robots to navigate the maze and try to score points in Park, we're not asking you to write an algorithm like this because it can be kind of tough, right? So if you want to, there's no issue if you want to hard code it, right? Hard coding it, it's not that hard, right? You know the robot needs to go straight here, left here, forward here, left here. You know, you just take your time and you'll get it no problem, and you might score more points than someone who decides to go the fancy way. So that's up to you. But yeah, so in essence, this is how things are done in the world of sensors and autonomous navigation.
Now, I would
Um,
like to add on something here about mazes. So this is known as a connected maze. As you notice, all the lines are connected to the outer wall at some point. Now, the difference between this maze and the challenge that we're doing is we have something known as a disjoint maze. In ours, you may notice that the obstacles are just floating in midair, or not midair, but they're floating in random space. They're not connected to anything. So this particular algorithm will not work for the challenge. But this is a demonstration on how you can implement sensors to detect said objects.
Exactly. And I guess one handy thing that you might want to know is that when you're playing with VEX Code VR, if you click this button here, it's activated automatically. But if you click this button here, you have all the data to you. So let me restart it and run it. You can see the rotation of the robot in degrees. You can see the front eye when it detects an object in front of it, or the down eye, and also the color that the eye sensors detect, as well as the location. And also the bumper. If you choose to use the bumper to detect maybe walls or objects, you have that as well. Yeah, so as you can see here, we have this while loop here. Uh, it's just like a loop that when it doesn't detect red, it just runs the algorithm, right? So doesn't see object, or if it doesn't see an object, it goes forward and turns. If it sees an object, then turns again. And then otherwise you turn left, right? So it doesn't run into a wall. So there you have it. Okay. Let's move on to our second activity, unless Clay, you might have some extra remarks.
I guess I do.
Okay.
As you can see as a code right here, this is actually a bad way to code. Not for the fact that it's written wrong or anything, But you might be looking at this and saying, I can't really follow this. I'm kind of lost. Well, something we like to put in as a programmer is known as a comment.
Right.
Daniel, would you like to show us what a comment is and how it
Sure
works
thing.
exactly?
And thank you for bringing that up. So comments are a pretty useful tool for programmers. Not just when you're programming yourself, but especially if you're programming in a group, if you're part of a team programming project. Comments will let you just insert comments, insert like notes in your project to just remind you of what you were trying to do when you're writing the code, or to remind others when they're reading your code. So one thing that Clement said at the beginning is that if you want us to point the optical sensor downwards on our physical robot, we would like you to add a comment. So let's say this is your code and you programmed it so that it works when the optical sensor is pointing downward. That's the sensor that detects color, right? So let's say you want that. Then you can say maybe please orient optical sensor downward, or something like that, right? And then we will see that, and then we'll do that for you when we run it on the physical robot on the physical map, right? But other than that, in just general usage, in general day-to-day programming, it is highly recommended that you use comments to explain what you're doing. So let's see, where can I put a comment for an example? Let's put a comment right before the while loop, so you can explain what the while loop does, right? So you can say, while the robot has not reached the parking spot, run the right hand rule. Run the right hand rule until it reaches the parking spot, right? No, that's too many letters, but there we go. This is a super super high level overview of what this while loop does. But when you're programming, you can go more into detail. You can put another comment that says in detail, like this makes it so that it doesn't run into a wall the third time, or something like that, right? So yeah, so there you go. Something very handy. Comments. They don't actually affect your code. So when you run this, the compiler skips right over it. It doesn't actually execute it. It's just there as a note. That's all it is. Okay. Now we have a challenge for you guys. So we have an activity. So if you guys could go to VexCode VR, I'm gonna open a new tab of VexCode VR. Oh, how do I delete this?
Just delete it, like completely delete it. Yeah. Or you can save it. You can just show them how to save. That works too.
Oh yeah, right. Yeah, so to save this, you would go to File here, save to your device, and then you will be able to save it just as a VexCode VR project. And then when it comes time to send it to us, you'll send us this file, and we can open it and we can load it onto the robot. So yeah, so now I'll have to try to figure out how to delete this.
Just click the things underneath it. Don't click the start.
Oh yeah. Oh, there we go.
Throw it away. There you go.
Okay.
Oh, hey. Let's
So
see
for
the new
this,
activity.
yeah, so for this activity, we're going to be using disk maze. So we encourage you to follow along. Like if you're sitting in front of a computer and it's convenient for you, open up a tab in your browser and go here and open up the disk maze, and so you can try the activity yourself. So the objective of this activity, we challenge you guys to write a program, and it's going to have to be using sensors. Write a program that makes the robot navigate to each of these blocks. So you have these green ones, blue ones, and red one there, down here. We want you to navigate each of these blocks one by one until you reach the red one, and then the robot stops. So let me maybe give you guys a hint. So for example, you want the robot.
Daniel, do you mind if I take this one?
Oh yeah, sure, go ahead.
Yeah, I'll share my screen and we shall get into this one.
Sure.
Thanks, Daniel.
Yeah, no problem.
Okay, so we've got our disk maze. Come on, disk maze. That's not a disk maze. So to get there, just select the playground, go find the disk maze, which should be right here. And we have our disk maze. So first of all, let's take a look at our map. The first thing that we like to understand when we take a look at any type of maze is we've got to take a quick look and see what clues we see. It might not look like much, and to be fair, when we looked at this, we had no clue what to do. But what do we notice here? We've got blue and green tiles. And we've also happened to have a red tile down in the corner. Daniel, can you confirm with me that you can see the map?
Yep, I can see your screen.
Now, this activity is designed so that you are supposed to solve this with a robot on its own. Now, that means the blue and the green tiles must mean something. So, what can we do here? Well, let's take a quick look. Now, in order for the robot to go through all of these checkpoints on its own, we will need a simple forever loop. Because we do not want the robot to ever stop. We're going to have to keep on going, keep searching, keep checking, keep checking, keep checking. Obviously, we need to tell the robot what do we do if we find green or blue. So we've got our friend, the if, else, and if, else, if block. This is another block that you will need. Additionally, we are going to need to tell the robot what each color represents. So we are going to go and find our objects. So we can use the front eye or the down eye. In this case, you can use either one. I will use the front eye. And I will tell it, okay, if you detect green, do something. If you detect blue, do something else. If you detect the red one, do something else again. Now, it's up to you. My challenge to you is, can you figure out what's missing in this code to make the robot navigate? We will give you a few minutes. You can message us in the chat or speak into the microphone if you want any assistance. But as of now, you are free to give this a try, and let's see how far you get. And if you do figure out how to solve it, we'll be happy if you tell us how. Now, I technically do have the answer sitting beside me, but I will not show you that answer. Good luck. So we're going to give you guys about 10 minutes to give this a try on your own. If you do solve it, give us a shout, give a chat, and let us know. And every 5 minutes or so, I am going to put in some blocks. So the next block will be coming in at 2:52, and I will start filling in a little bit to help guide you guys and see if you're on the right track. You might hear that it is very silent in this room at the moment, but this is not the sound of silence. This is sound of everyone thinking how to solve this puzzle. What is the goal? Well, the goal of this puzzle is you're trying to create a code that uses the green and blue blocks to navigate the robot without any instruction other than your code to get to the red end zone. There's one little red piece in that bottom right corner that you're trying to get to, and the only code that you require is using these blocks and adding some more blocks to it. Basically, it's a fill in the blanks activity. You are trying to fill in this code to get the robot from the starting point to that red endpoint. Mm-hmm. All right. 5 minutes has passed, and I shall add a block to our code. So we know that we want to do something when we get to either the blue tile or the green tile or the red tile. So if nothing is detected, you will want the robot to simply just drive forward and keep driving forward until you detect something. So what does this do right now? Well, nothing is detected. The robot keeps driving forward. Simply enough, that's all that it does so far. Yeah, trying to get the number right without the grid is painful. Indeed, it is. That is actually what makes this maze so challenging. It does not have a grid. However, the places that the sensors trigger is actually quite useful. Now, I guess I can help that. Some blocks that you will require are drive backwards for 40 millimeters and drive backwards for 40 millimeters. And this block drive forward for 60 millimeters. So what happens now? Well, the robot drives forwards, detects a green block, and backs up. Now, it may look like it's not doing much, it's just going back and forth here. But if you notice, when it does reverse, that 40 millimeters will line it up with the next target right beside it, the blue marker. So the goal is not to get the robot from start to finish without a grid marker. Your goal is to use a little bit of fine tuning here and there to get the robot aligned with the next place you might want to get to. If we think about it, looking at this map, we've driven our robot all the way till we got into that first green marker. Ooh, David has finished. Okay, David. All right, hang on to that thought. We've still got a few more minutes for the rest of us. We'll give you guys about 2 more minutes. And in the meantime, yeah. Well done, David. All right. In the meantime, while you guys are still solving, David, you can type in the chat, what am I missing from my detection for green? So if the front eye detects green, what should my robot do? Now that you have solved it, let's see. All right, turn right for 90 degrees. Excellent. Let's see what happens. All right, we've gotten to another location. Nice. So we'll probably have to get to another block. So now we are at a blue block. This is not the same as the green block. Does anyone else know what's the next step? We are now at this part of the code where the front eye has detected blue. We're missing something in the code still. Does anyone know what it is? Turn 90 left. Natalie, that is correct. So the next part of our algorithm is turning left for 90 degrees. All right, now that it's filled in, let's see what happens. All right, second objective. Nice, we got through 2 of them, 2 down. Nice, third one. Fourth one. Very good. Getting there, almost done. Excellent, we've gotten to the red block, but now our robot never really stops moving, does it? Well, a code in a forever loop will basically run forever. So there's actually one more block in here that we have to use that we did not cover yet, but it is known as the break or stop project. Break will just break the code, or stop project. So we'll just chuck in a stop project code in here. And if we restart the code, it'll stop at the very end because the entire code stops. The fact that the robot is not perfectly lined up with the disks bothers me. Oh yeah, that bothered me too when I was designing this activity. I had to solve this for myself. Vex doesn't give you the solutions. In fact, you can do any of the tutorials and they don't actually tell you what the final solution code was. So driving in backwards 40 millimeters took a little bit of testing and massaging to get it to work. But nicely done, guys. You guys did it. Ignore my little goof there. That should have been drive forward for 60. It should stop in the red square, but you guys got the point. So congratulations to those who have finished this activity. And for those of you guys who just solved it now, well, don't worry, you still got the challenge to show off your skills. Ooh, so you use a repeat until not, down eye detect. That's clever. That is a very good touch, David. So what David has done here is he's used a not logic gate to use the bottom eye. So as soon as the bottom eye leaves this little square, it should be aligned with the next one, is what he has done. So like I said, there is no true correct answer for coding. Excellent work, everyone. And that is an excellent activity for everyone. I hope you guys enjoyed it. That is actually the end of this presentation. So thank you so much for joining. And we'll open the floor now to questions. The Surreal team will remain for another 10 minutes or so, but we hope you have enjoyed this second workshop. You are free to keep playing around with VexCode VR. We're here to answer your questions, give you any assistance, and thank you for tuning in. And we wish you an excellent rest of your Sunday weekend.
Yep, and I would also like to add that that the code submissions are actually due next week, right, Clay?
Yes, indeed.
Indeed. So since we're expecting you to submit your code next week on the 21st of August, if you have any questions about, if you have any, just have any questions or need clarification on anything related to what you need to do to solve the maze, just ask us now, because we realize that next week will be the deadline. Clement, could you go to the slide with the maze?
Yes, sir. Here we go. Oh, which maze? Our map, right?
Yes. Right, yeah. So just to recap here, because this is the last time that we are having a workshop before you are submitting your code. So, or maybe we'll make it so that you can submit it after the third workshop, so then we can help you as well.
Yep, we can give them another day or so. We'll see how far you guys are. If you guys want another day, an extra day after that deadline, let us know, shoot us an email, and we will let you guys know.
Where on the robot is the color sensor facing down? It would
It is
be
in the same place. It's just it's basically at the very front of the robot, just
Yep.
like or I guess Daniel, you have the robot physically, so
Yes, yeah, I can show. So hold on. Here. So color sensor is facing forward. This one is facing forward at the moment, but we're going to make it so that if you want the sensor to face downward, we're just going to have like a mechanism so that this thing right here, it would still be at the front of the robot, but it would just be facing downward like this. All right.
all right, you're welcome. Thank you, Daniel. And thank you for the excellent question, Natalie.